What if the red face of Mars were a mask, a carefully painted facade that hides a complex life beneath? What if the planet that has been cataloged in textbooks as cold, dry, and dead were, in truth, a carefully maintained stage set for a drama unfolding far below the surface? The question alone is a small, destabilizing thing, a single hypothesis that stretches the seams of how humans look at worlds beyond their own. For generations, the image of Mars has been simple and sure. A rust-colored orb hung in the night sky, its surface pocked by craters and carved by ancient channels, its thin, whispering air incapable of sustaining the sorts of life that flourish on Earth. That narrative is built on decades of telescopic scrutiny, photographic mosaics taken from orbit, and the slow, intimate work of rovers that have trundled across its regolith like tireless anthropologists. The scientific verdict has been repeated so often that it has become a kind of cultural weather. Mars is arid, cold, irradiated. It is a dead sibling to Earth, interesting for its history but not its present vitality. Yet the proposition that a civilization could be thriving in Mars's core is not merely an exercise in imagination. It is a thought experiment that probes the limits of human perception. What does it mean to say dead when one has only ever had eyes for the surface? What sorts of life and what sorts of societies could exist in the sharp, unseen gradients of temperature, pressure, and chemistry that lie beneath a planet's skin? The Great Deception is not an accusation directed at any single mission or discipline. It is a description of the biases baked into observation itself. It is the awareness that abundance can exist in places humans cannot easily touch or see, and that assumptions made from a distance can be spectacularly, humblingly wrong. To understand how a civilization might remain hidden, the first step is to recognize the peculiarities of planetary observation. Remote sensing tools, spectrometers that read the fingerprints of molecules, radars that ping the shallow depths, and cameras that map albedo across latitudes are excellent at reading surfaces. They excel at reporting what photons have bounced off or what radio waves have been reflected back. But these instruments are, by design, sensitive to the outermost layers. Heat signatures from deep within a planet can be muffled by kilometers of insulating rock. Chemical bouquets rising from subterranean vents can be absorbed and altered before they reach the thin atmosphere. Seismic waves are messy, and without a well-distributed network of sensors, their sources are ambiguous. The silence of one method. Imagine, then, a civilization that grew not under planet-side skies, but under pressure and magma, shaped by the steady, relentless rhythms of planetary geology. Its technologies would be adapted to gradients that humans rarely sample: the slow creep of mantle convection, the whisper of electromagnetic noise in the high-pressure environment, the slow chemistry of deep mineral cycles. Energy, instead of being drawn from sunlight, would be harvested from geothermal gradients, from the decay of radioactive isotopes, from the chemical disequilibria that form where rock meets rock. Communication might occur in frequencies and modalities that do not readily leak to the surface. Mechanical oscillations transmitted through rock, fields confined by dense materials, or even patterns in code. Survival, in this context, could be the central motive behind deception. Planets experience cataclysms on timescales that dwarf individual lifespans: giant impacts, global glaciations, atmospheric loss. A civilization that has watched surface climates swing like pendulums across eons might have learned that the thin, exposed crust is a dangerous place to commit durable infrastructure. The core, insulated by kilometers of rock, is a refuge from the whims of suns and cosmic punctuation. A species that intends to endure across geological epochs might therefore choose concealment not as a moral decision, but as a practical calculus. To hide in the deep is to hedge against extinction. There is also a subtler form of deception that arises not from malice, but from engineering elegance. A civilization could purposefully modulate the outward signs of its existence so as to appear as part of the planet's geology, altering heat fluxes to mimic background geothermal patterns, seeding isotopic signatures that read as abiotic, or maintaining a crustal cloak of oxidized iron to blend with the familiar red. The effectiveness of such camouflage would derive from the expectations of external observers, humans who have modeled planets in tidy ways and have limited ways to test those models. The Great Deception, then, becomes a dialogue between two kinds of intelligence, one that understands the planet intimately and one that reads it from a respectful but necessarily distant. Humanity's emotional response to the possibility is complicated. To some, the idea of a hidden civilization is thrilling, a confirmation that life, and perhaps intelligence, is not constrained to the narrow conditions seen on Earth. For others, it is disquieting. The image of being wrong about an entire planet is a small, persistent erosion of confidence. It forces an admission that human instruments and interpretations are provisional. They are approximations built from finite data and imaginative extrapolation. That humble sensation, this discomfort at our limits of knowledge, is itself valuable. It is the feeling that compels better instruments, wider collaboration, and more The history of thought about Mars has, in fact, been a history of correcting for human bias. The 19th century craze for canals on Mars, lines that telescopic observers interpreted as signs of engineering, was not just an error in observation, it was an error in interpretation born of a desire to see other minds. Later, spacecraft and rovers refined, corrected, and sometimes shattered earlier narratives. Each act of observation trades older certainties for newer ambiguities. Staring into Martian regolith, humanity has always been looking for echoes of itself. If it fails to look for the alien forms adapted to different niches, deep thermal gradients, rock-hosted ecosystems, it may repeatedly misread the planet's true nature. Technically, there are plausible routes for life to exist in the deep. On Earth, subsurface ecosystems teem far from sunlight, microbial communities living in cracks and pores of rocks, chemosynthetic webs that derive energy from sulfate reduction or hydrogen produced by serpentinization, and fungal and bacterial life that forms slow, persistent biospheres in the deep. If a planet has enough internal heat and the right catalytic minerals, life can find a foothold. A civilization, in this context, might be built from such life, amplified through collective organization and technological innovation adapted to a subterranean milieu. Their machines might be grown from mineral biohybrids, their information storage might be encoded in slow-changing crystalline lattices, and their social. These differences have consequences for detectability. Consider the instruments humans typically deploy to look for life. Orbital spectrometers tuned to signatures like methane, rovers that sample surface soils, thermal imagers that map surface heat. A civilization living in a core could control or attenuate the very biosignatures these instruments seek. Methane emissions could be trapped or channeled into mineral sinks. Thermal anomalies could be smoothed by engineered conduction. Signals meant to be private information transmission, power distribution, could be bound to conductive paths in rock that do not radiate into space. Even the electromagnetic footprint might be suppressed by the deliberate use of frequencies absorbed by the surrounding mantle. The technological analogy is simple. There is also a temporal camouflage to consider. Human probes and telescopes are snapshots in a timeline that is both principled and painfully brief. Civilizations that measure themselves in hundreds of thousands to millions of years have the luxury of temporal invisibility. They can hide by moving slowly, by making changes only on timescales that human missions cannot easily resolve. Geological processes operate at rates that would be imperceptible across the decades of a mission's operation. In this sense, the Great Deception is not always an active conspiracy, but can be the passive result of differing timescales. What is visible to a sentient observer with a life measured in years is invisible to entities that think in millennia. Yet speculative scenarios can also be productive. The thought that Mars could harbor a living interior forces a rethink of exploration strategies. Instead of only sending rovers to sample the surface, it becomes sensible to deploy instruments tuned to the deep, dense seismic networks that can resolve fine-scale structure, neutrino or muon detectors that can peer through rock, boreholes drilled kilometers down to sample pristine subsurface waters, arrays that can detect low-frequency mechanical modulations indicative of engineered activity. There is poetry in that shift, an entire program of curiosity reoriented from the skin to the bones of a planet. It is a sober realization that the most transformative discoveries may not be those announced with grand, surface-facing. Beyond instruments, the possibility of a hidden civilization asks for a philosophical shift. The search for extraterrestrial intelligence has often been framed in ways that reflect human values, radio beacons, intentional signaling, visible megastructures. A core-dwelling civilization would challenge that anthropocentrism. It would suggest that intelligence does not always seek the skies, and that survival strategies can prioritize hiding over heralding. That realization complicates the moral calculus of contact. Would a civilization that has deliberately hidden itself welcome a revelation? Would humanity be equipped to interpret, much less to communicate, across such different material, temporal, and ethical frameworks? And what of the moral dimension for humanity? The Great Deception is not merely about being wrong, it is a mirror held to human tendency to simplify and to narrate. It demands a kind of epistemic humility, the readiness to accept that the absence of evidence is not evidence of absence, and that a comfortable narrative of planetary death may be a story of human convenience. It also presses on terrestrial anxieties. If life can hide so thoroughly on Mars, what might Earth hide in its own deep past? The notion sits uneasily with the modern myth that human history is the primary event of planetary time. Deep time is indifferent to announcements. It records and erases in ways that will always be partly opaque to observers who live only for a breath of planetary youth. There is, finally, an aesthetic element to the deception. Concealment is a kind of artistry, a subtle craft of blending living processes into geological rhythms. The possibility of a civilization that creates beauty not for spectacle but for survival is haunting. Its monuments would not be towering spires or luminous beacons, they might be slow, elegant rearrangements of mineralogy, carefully tuned gradients in heat and chemistry. The choreography of fluid flows through fractures. For outsiders who only know spectacle as the currency of civilization, such silent craftsmanship would be invisible. To appreciate it would require a different sort of attention, a patient listening for patterns in the hum of a planet. The Great Deception, then, functions on several levels: technical, epistemic, emotional, and ethical. Technically, it highlights the limits of instruments and the clever ways a subsurface civilization could be missed. Epistemically, it challenges the assumptions that undergird the search for life. Emotionally, it provokes awe and discomfort in equal measure, collapsing certainty into a manageable, productive anxiety. Ethically, it asks humanity to consider how it would respond were the mask lifted, whether with humility, fear, or the reflexive urge to claim dominion. If Mars is a planet wearing a mask, that mask will not be torn off by sensationalism. It will be removed, if at all, through a patient, multidisciplinary campaign that pairs better instruments with a willingness to let go of old narratives. The Great Deception is not a final verdict, it is a challenge and an invitation. It asks humanity to expand its notion of where life might hide, to retool curiosity for depth as well as breadth, and to remember that the universe often prefers its secrets to be subtle. What if the hollow idea were not merely an eccentric footnote in the history of speculation, but a literal possibility worth testing? What if beneath the familiar rust and dust there existed a cavernous heart, a space large enough to cradle an ocean, an enclosed sea ringing a core of stone and metal, isolated from the light and from the casual gaze of orbiting cameras? That image, an ocean under kilometers of rock, reframes Mars not as a dead husk but as a layered world with secret interiors. It is a small, destabilizing image, and it invites a very particular kind of curiosity, the curiosity that asks not only what is seen, but what might be concealed by mere geometry. For centuries, thinkers have toyed with the notion of hollow worlds. At different moments in history, scholars and mavericks alike sketched possibilities in which planetary interiors were not simple balls of homogeneous rock, but complex, cavernous realms. On Earth, such ideas were eventually constrained by measurements, mass, moment of inertia, seismic traces. For Mars, though, the measurements have been thinner, the dataset more recent, and the room for imagination correspondingly larger. Some scientists, not in a conspiratorial sense, but as an exercise in theoretical openness, have asked whether a cavernous interior could exist that still fits the broad constraints imposed by a planet's mass and bulk density. Those hypotheses do not deny rock and iron, they propose that cavities, voids, and fluid-filled chambers. To imagine a hollow sufficient to hold an ocean is to imagine a geometry that plays with averages. A planet's mean density is a blunt number, it tells how mass is distributed in total, but not precisely how it is patterned in 3 dimensions. A thick, dense shell of basalt and iron surrounding a lower density central region, whether because of partial melting, compositional stratification, or engineered excavation, could, in principle, mimic the gravitational signatures of a more uniformly composed planet. The trick is that gravity and inertia speak in averages. They are blunt instruments. A hollow can hide within the margin of error if its mass is compensated elsewhere, if anomalies are smeared across layers, or if localized anomalies are smoothed by observational limitations. That is not an argument. If such a cavern existed, how could an ocean persist there at all? Water under tens or hundreds of kilometers of rock behaves differently than water under a sky. Pressure rises rapidly with depth, and temperature gradients are complex, but planetary interiors also host processes that can make water both abundant and stable: radiogenic heating from decaying isotopes, residual heat from accretion and differentiation, and frictional heating from tectonics or tidal forcing. Even with a thin atmosphere and a cold surface, a localized subsurface environment can maintain temperatures and pressures that support liquid phases. Salts and dissolved chemicals depress freezing points. Under the right mixture, water can remain liquid at temperatures far below the surface. There is physical precedent for life in darkness on Earth. Oceans beneath ice shelves, hydrothermal vents on abyssal plains, and vast biospheres within fractured basalts all testify to ecosystems that do not depend on sunlight. Energy can be harvested from chemical disequilibrium, where hot rock meets cold water, from redox gradients created by serpentinization, the reaction of ultramafic rocks with water that produces hydrogen, from radiolysis splitting water molecules, or from gradients in mineral composition. In a sealed, subsurface ocean, the flows are slow, the cycles long, and the chemistry patient. Organisms that arise there, if they do, would live to geological rhythms, generations measured in seasons of mineral deposition, ecological shift. The possible ocean would not resemble any parkland seascape. It would be an underwater world beholden to stone. Its shorelines would be the undersides of ledges of basalt, its currents the slow oozing of fluid through networks of fractures, its light a dull glow perhaps generated by chemiluminescent microbes or by geothermal fluorescence. Mountains would be replaced by mineral chimneys, continents by columns of crystalline precipitate. Above this quiet sea, rock would press like a ceiling. The concept of a horizon would be inverted. To imagine it is to invert a human habit. The horizon that usually offers openness would become a confining, protective lid. An ocean under rock suggests particular forms of organization. Energy is local and must be distributed. Nutrients are tied to slow mineral cycling. Life, if present, might cluster around seams where geochemistry is active, the equivalent of vents and seeps. Complexity would be possible where gradients are steep and persistent. In the slow twilight of such a world, solutions to ecological problems would look different. Transport and communication might rely on mechanical channels carved through rock, on chemical waves propagated through pore spaces, or on networks of filamentous organisms that mediate mineral flux. The timescales of change would favor stability and redundancy. Organisms would likely prioritize resilience, repair mechanisms, communal storage. That description invites an awkward conjunction of ambition and humility. The science is concrete in its outline: heat, pressure, chemistry, fluid dynamics. Yet it is speculative when it comes to life and society. Any extrapolation beyond microbial ecosystems quickly moves away from empirical constraint into the realm of possibility. The task for a thoughtful investigator is not to declare certainties, but to expand the observational agenda, to ask what kinds of instruments and missions would make a subsurface ocean plausible or implausible. How would one detect such an interior from the outside? Gravity mapping can reveal mass anomalies, but its resolution diminishes with distance and time. Orbital radar can peer beneath thin regolith and detect layers of ice, but its penetration through thick basalt is limited. Seismology, listening for Marsquakes, offers a powerful probe of internal structure, but it requires a distributed network of sensors to triangulate sources and image subsurface discontinuities. The InSight lander's seismometer on Mars already demonstrated the radical difference that listening can make. Its handful of detections created a first contour map of Marsquakes, yielding hints about crustal thickness and mantle properties. Yet a single instrument, fixed to a single spot, can only suggest. Other methods are more exotic but conceptually elegant. Muon tomography, a technique borrowed from particle physics, uses naturally occurring high-energy particles that penetrate rock to reveal density contrasts. Neutrino detectors, still in their adolescence for planetary science, can in principle image deep interiors by detecting weakly interacting particles that traverse entire planets. Electromagnetic sounding measures how induced currents decay through a planet, giving insight into conductivity and the presence of fluids. Each method has trade-offs of resolution, cost, and technological maturity. The strategic question becomes one of redundancy. If the hypothesis of a hollow interior is worth testing, multiple complementary probes must converge to build a coherent. The possibility of a subsurface ocean raises another, more unsettling question. Could such an interior be intentionally obscured? The idea is more philosophical than conspiratorial. A natural system can masquerade as abiotic. Chemical signatures can be altered by mineral sinks. Thermal anomalies can be damped by conductive layers. Emissions can be absorbed by porous rock. Even biological activity itself can be tuned, by natural selection or engineering, to minimize leakiness. The notion that a planetary interior might be quiet because it is inherently quiet, not because it is uninhabited, forces a rethinking of the criteria for life detection. In the end, the problem is an epistemic one. It is easier to mistake silence for absence than it is to show silence is deliberate. Emotionally, the hollow hypothesis acts like a mirror. It reflects back humanity's tendency to equate visibility with reality. For centuries, cultures have equated beams who leave obvious signs, towers, beacons, radio transmissions with intelligence. There is comfort in the bright and the noisy. A hidden ocean offers the opposite, a slow, subterranean existence indifferent to performance. That thought nudges at a deeper humility. If life can persist without spectacle, then the human search must become more patient, more methodical, and more willing to be surprised. The aesthetics of a subsurface ocean are strangely poignant. There is something almost romantic in the image of a vast, enclosed sea that witnesses eons of planetary change from beneath a lid of rock. It is a repository of continuity, a place where chemical memory accumulates, where relics of past surface climates might be preserved in salt layers or clathrates, where the slow sweep of mineral deposition keeps a ledger of epochs. To humans raised on visible histories, artifacts, ruins, chronicles, the notion of a sealed archive is alluring. It tempts the imagination with the possibility of discovering traces of earlier planetary habitability or even of vanished surface ecosystems preserved in the quiet sedimentary record of a subsurface. Yet that romantic impulse must be balanced by a sober assessment of risk and method. Drilling into a subsurface ocean would be an act of profound disturbance. Contamination, the introduction of Earth microbes, is not merely a technical mishap, it would be an ethical rupture. The planetary protection frameworks that guide exploration already recognize the need to avoid introducing terrestrial life to pristine environments. The scale and consequences of breaching a sealed Martian sea would be orders of magnitude larger. If such an ocean exists, the decision to sample it would require international consensus, extreme sterilization protocols, and ethical deliberation akin to decisions about deep-sea mining or genetic repositories on Earth. On the other hand, passive detection has its own moral arc. To watch and listen without intruding is a choice too. It is a recognition that some discoveries may be worth the patient accumulation of evidence. It is a choice that honors epistemic humility, that accepts the slow accrual of knowledge rather than the quick publicity of a rushed claim. It is also a choice that aligns with the deeper rhythms of deep time thinking, that planetary histories are long, and that the most consequential revelations may come not from dramatic forays, but from the quiet persistence of careful observation. The Hollow Mars hypothesis, then, is not simply a technical curiosity. It is a conceptual reframing that forces an expansion of both instruments and ethics. Technically, it demands more sensitive seismology, novel particle-based imaging, and careful gravitational mapping. Philosophically, it asks humans to broaden their categories of what counts as life and where it might thrive. Emotionally, it reintroduces a sense of smallness, the sense that a planet can hold secrets beneath its skin, and that those secrets might survive the arrogance of short-lived observers. In a more metaphoric register, the idea of an ocean beneath rock is a reminder that planets are not merely surfaces to be scanned, but layered archives. Each shell, crust, mantle, core preserves different kinds of history. The outermost layer records meteor showers, wind, and water on human timescales. The interior records tectonic churn and the slow balancing of isotopes across epochs. The potential presence of an underground sea on Mars dramatizes the lesson of deep time, that life, if it takes hold, will find niches where persistence trumps flashiness. It is a planetary hum beneath the scream of headlines. Ultimately, the Hollow Mars hypothesis functions as a methodological provocation. Even if the idea proves incorrect in the strictest sense, pursuing it refines the tools and the sensibilities of planetary science. It encourages missions that listen as well as look, that probe as well as peer, and that place a premium on the patient accumulation of evidence. It also enlarges the ethical conversation about whether and how to disturb worlds that may have been quietly sustaining processes for millions of years. In that way, the hypothesis becomes part of a larger lesson, that exploration is not merely the conquest of new space, but the cultivation of a new kind of attention, one tuned to depth, to subtlety, and to the humility. What would Mars sound like if it had a secret to keep, not a silence, but a signature, a peculiar ringing that could only come from cavities in airs sealed beneath stone? The question at once reframes an ordinary seismogram. A diagram of squiggles becomes a cryptic conversation, a faint late arrival, a prolonged tail, a frequency peak where none was expected. These are the small anomalies that, strung together, begin to suggest that the planet's interior might be speaking in an unfamiliar tongue. Seismic instruments placed on Mars over the past decades have, intermittently and inexplicably, recorded such voices. Not every quake produces them. The echoes are rare, like accents in a language that otherwise sounds like steady geologic prose. When they do appear, they refuse to fit neatly into the catalog of expected rock behavior. Instead of the crisp P-wave arrivals or the predictable S-wave reverberations carved by solid rock, some traces show coda waves that persist in frequencies reminiscent of a struck bell, long-lived, narrow-band oscillations that decay slowly. Some records display delayed secondary pulses, arrivals that have lost the directness of a wave passing through layered basalt and instead arrive as if having meandered through hollow corridors. On Earth, such acoustic curiosities have correlates in familiar places, caves, karst systems, underground caverns whose acoustic signatures betray their hollowness, lava tubes that resonate when wind and waves push air through their mouths, abandoned mines that ring like giant gongs when impacted. The physics is simple and eloquent. An enclosed volume bounded by rigid walls supports resonant modes. When energy from a Marsquake, an impact, or thermal cracking excites the cavity, the trapped fluids or gases can set up standing waves. Those standing waves persist and interfere. The resulting seismogram carries a fingerprint of size, shape, and the properties of whatever fills the void. Read in that way, a particular kind of seismic signal becomes a map maker's hint. Narrow-band resonances imply cavities with specific characteristic dimensions. Extended coda waves imply scattering from multiple reflectors. Low-speed, long-wavelength signals suggest that the medium through which the waves traveled was not solid rock, but rather a low-density pocket, perhaps filled with gas or fluid. The frequency of a resonant peak scales inversely with the size of the cavity. A bell-like ringing at a fraction of a hertz points to structures measured in kilometers rather than meters. Thus, a single anomalous trace can be the slender thread that, when combined with others, unravels the ordinary reading of a planet's internal architecture. But inference is never straightforward. The subsurface is a messy medium. Heterogeneities, fractures, and anisotropic materials scatter and entangle waves. A signal that looks like resonance could be the interference of waves scattered by a cluster of voids, or the consequence of a highly cracked basaltic layer saturated with volatiles. Seismic records from a single station are especially ambiguous. They are, in effect, the projection of a complex three-dimensional reality onto a single line of sight. Detecting true cavities and distinguishing them from simple geological noise requires networks and techniques that can triangulate and synthesize information. This is one reason the odd echoes recorded on Mars garnered such attention. They were not numerous, but they were persistent enough and peculiar enough to survive the noise of instrumentation and the cautious instincts of interpreters. Spectral analyses showed unexpected concentration of energy at particular frequencies. Polarization studies suggested that the particle motion in those arrivals was inconsistent with simple shear or compressional waves through homogeneous rock. The coded decay rates were longer than predicted for a purely ductile mantle. In short, the math did not want to behave like familiar geology. Interpretation opened into a set of unsettling possibilities. One was the prosaic lava tubes. The subterranean conduits carved by flowing molten rock are ubiquitous on basaltic worlds and can extend for tens of kilometers. They can be acoustically resonant and could explain certain signals. Another mundane hypothesis centered on buried ice. Ice-rich layers, particularly if punctuated by voids or layers of regolith, produce complicated seismic responses that can mimic resonance. A third possibility was that a highly fractured crust, riddled with porous networks saturated with volatiles, could scatter waves to produce long coda tails. Then there was the more provocative interpretation: cavities large enough and configured in ways that, if filled with gas or fluid, would support acoustic resonance in the manner recorded. Such cavities would not only change how Mars sounded, they would reframe the planet's internal topology. They could be empty chambers with trapped atmospheres, sealed basins with slow-moving brines, or connected labyrinths of void space beneath the basaltic skin. In the speculative ledger that had been opened across the previous parts of the investigation, hollow interiors, underground oceans, deep, sheltered habitats, these signatures read as a possible corroboration. If the echoes were indeed produced by large hollow spaces, then the dead, rust-colored exterior, even the suggestion that cavities could hold an atmosphere, challenges a basic instinct about planetary environments. The surface of Mars is thin and cold, sustaining a robust atmosphere for life, as humans commonly imagine it, seems impossible there. But atmospheres do not have to be global to be significant. A sealed subsurface chamber could trap a locally buoyant, compositionally distinct atmosphere. Pressure within such an enclosure could be higher than the outside by several orders of magnitude if the rock above forms a competent cap. Outgassing, radiogenic heating, or chemical reactions at the chamber walls might replenish or maintain that internal air. In the late echoes on seismograms, the speed of sound implied by certain resonant frequencies might. The implications are both technical and existential. Technically, if there are pockets of low-density material at depth, the global models of Mars's interior must be revisited. Gravity and mass distribution estimates, previously smoothed into a tidy picture of a dense mantle, would need local correction. Thermal models, which depend intimately on how heat is transported through conduction and convection, would be recalibrated because voids and fluids alter thermal gradients and pathways. More than that, an existence of cavities changes expectations about the planet's hydrology and volatile cycles. Closed or semi-closed basins can sequester water and gases for epochs, acting as time capsules. The discovery of such repositories would reconfigure questions about Mars's capacity to harbor life, the record. Yet the emotional dimension is no less significant. The scientific community's reaction to these seismic irregularities has been appropriately mixed: curiosity, skepticism, a cautious thrill. Curiosity because the possibility reopens questions deemed settled, skepticism because extraordinary structural claims require extraordinary evidence, thrill because, in the right circumstances, a planet's whispers could be the first hint of an interior world that is more active and less sterile than assumed. These are not merely professional sentiments. They map onto a deeper human relationship to discovery, the oscillation between humility and audacity. To listen and wonder is the more modest path. To announce certainty prematurely is the hazard of narrative hunger. Methodologically, the path forward is clear and also challenging. To discriminate between competing hypotheses requires more listening, with better ears and from more locations. Dense arrays of seismometers would convert ambiguous lines into three-dimensional images. Ambient noise tomography, a technique that treats background seismic hum as a source of illumination, can reveal contrasts in velocity and attenuation that passive quake catalogs cannot. Active seismic methods, where deliberate energy sources are used to probe structure, could provide controlled experiments, though they raise practical and ethical questions about disturbance. Particle-based imaging, once speculative, has also matured, muon tomography and neutrino-based methods, capable of penetrating kilometers of. Those risks are not merely technical. The ethical dimensions of probing sealed subsurface spaces are profound. If cavities hold distinct atmospheres or fluids, they may also host chemical or biological regimes that have been evolving insulated from the surface. Any intrusive investigation, drilling, blasting, or forced venting, risks contamination. The terrestrial history of exploration offers a cautionary tale. Human curiosity has frequently collided with fragile, irreplaceable systems. Planetary protection protocols exist precisely to mediate that tension. They are conservative by design, favoring the preservation of potential native ecosystems until evidence and consensus justify intervention. There is a final, more philosophical layer to interpret. These seismic echoes from beneath Mars force a recalibration of embodiment in planetary exploration. For a long time, humanity has equated visibility with existence. The surface, photogenic and accessible, has been the canvas upon which life and history are painted. But geology teaches a different sensibility. Most of a planet's mass, energy, and perhaps its liveliest processes are hidden. Seismic anomalies are a reminder that presence need not be noisy to be real. Quiet, slow processes. Trapped air moving through a cavern, slow brine circulation, chemical gradients that support tiny communities, can persist for millions of years. The echoes recorded so far will not settle the matter. They are alluring hints, fragile invitations to listen more carefully. Their interpretation will depend on patience and humility. Patience to build the networks and instruments that can corroborate the signals. Humility to accept that a short record of observations can yield many plausible models. Yet even as they remain ambiguous, the echoes have already changed the question set. They have expanded the scope of curiosity from, is Mars dead, to what might be living beneath what we can see, and how would we know? In the end, the most striking lesson is epistemic. Geological time favors concealment. Cavities and sealed atmospheres live on timescales that dwarf human campaigns. A resonant tremor, captured and recorded in a brief episode of human attention, is the planet's way of reminding observers of their brevity. The careful listener, endowed with tools and ethical constraint, can convert those faint signals into knowledge. But that conversion is delicate. It requires translating a seismogram into a story without overriding the silence that might yet hide other voices. The echoes from beneath Mars thus function as both clue and caution. They invite investigation while reminding listeners that some revelations require the slow accumulation of evidence, the pooling of methods, and a respect. What if the most intimate oceans of a planet were never meant to be seen? That they were arranged as archives and refuges, slow-moving and secretive, where water did not glint beneath the sky but flowed beneath the roof of rock. This image reframes what water on Mars has meant for a century. It changes the question from, was there ever water here, to, could water be here now, held in chambers so private they escape ordinary gaze? The thought carries a small electric charge. If water persists deep beneath the rust, then Mars is not merely a record of a wetter past. It could be a living, layered world with ecosystems that never learned to face sunlight. Radars is not a single dramatic headline, but a ledger of faint signals, clever inference, and instruments that have learned to listen for the planet's hidden signatures. Radar sounders aboard orbiters have peeled back the shallow skin of regolith and ice. Neutron detectors have mapped hydrogen anomalies. Thermal infrared maps chart the subtle ways heat escapes from deeper layers. Each technique reads a different part of the story. Where radar sees strong, flat reflectors beneath polar ice, neutron spectroscopy counts hydrogen as a proxy for water and hydrated minerals. Where temperature gradients suggest insulating layers, there is a hint that something with different thermal properties lies below. In 2008, a particularly bright radar reflection beneath the southern polar cap crystallized public imagination. Anomalous, localized, and sharply reflective in ways that invited one interpretation. Liquid water under rock behaves differently than water under air. The physics that governs its persistence is a negotiation between pressure, temperature, chemistry, and time. On Mars, where the surface is bone dry and atmospheric pressure is a whisper, water can survive in liquid form where conditions depart from the surface norm, in deep basins where lithostatic pressure rises, in salt-rich brines where freezing points are depressed, or where heat from the planet's interior keeps an interface above the melt line. The chemistry matters. Salts such as perchlorates, sulfates, and chlorides can dramatically lower the temperature at which water freezes. Under a thick cap of ice and overlying rock, these salts can combine with water to form stable, supercooled brines, liquids that would be unthinkable on the surface but entirely plausible in space. Heat is the other central element. For a subsurface ocean to persist, it requires an energy flux, slow, steady, and patient. That energy can come from several sources: residual heat from planetary formation, decay of radioactive isotopes in crustal rocks, frictional heating from tectonics or mantle upwelling, and localized heating from chemical reactions like serpentinization. On Earth, hydrothermal vents, places where hot rock meets seawater, support rich ecosystems in total darkness by supplying reduced compounds and a thermodynamic gradient exploitable by microbes. The analogy is not exact, but it is instructive. Life can be powered by gradients, not sun. If Mars retains pockets of sufficient heat and suitable mineralogy, those pockets could host chemo. A subsurface ocean would not be a neat planetary-scale sea. It would likely be patchy, sealed basins beneath polar caps, interconnected aquifers threaded through fractured crust, and isolated brine lenses locked within porous sediments. The topology would be dictated by geology, by faults and folds, by buried channels carved during a wetter epoch, by layers of varying permeability and caprock competency that could trap fluids for eons. Those pockets could be transient on geological timescales, slowly evolving as heat redistributes, fractures propagate, and salts precipitate. Yet, transient in deep time can mean millions of years. A reservoir sealed by competent rock can quietly hold its chemistry and its. The biological possibility of life in such settings is not a casual extrapolation. It is grounded in the existence of Earth's deep biosphere. Miles beneath continents and beneath abyssal plains, there are ecosystems that thrive in rock, sustained by chemical energy. Microbial communities colonize fracture surfaces, live in pore water, and cycle carbon and sulfur at rates that are glacial by human standards but sufficient for persistence. Metabolism can be slow, life can be small, and evolutionary time can be extraordinarily long. In a subsurface Martian ocean, if chemical energy and water coincide, something analogous could exist: chemolithoautotrophs that draw energy from inorganic reactions, biofilms that coat mineral surfaces, and slow webs of nutrient exchange mediated by isolation which shape biological form and behavior. Cut off from sunlight, visual signaling would be useless. Chemical gradients and mechanical disturbances would become primary channels of information. Life shaped by rock would evolve modes of interaction, alien to surface life: filaments that shuttle nutrients across meters of crust, mineral-associated metabolisms that store and release energy seasonally on timescales of centuries, and perhaps macroscopic structures built from precipitated salts rather than organic scaffolding. The ecology would be slow, layered, and intimate. What might look like barren geology to an orbiting camera could, at the microscale, be a dense tapestry of living and inorganic processes entwined. From the perspective of detection, the challenges are profound. A subsurface ocean, sealed and isolated, minimizes its leakage of telltale gases. Methane plumes from deep sources can be trapped or consumed by mineral sinks. Thermal anomalies from geothermal hotspots can be smoothed by conductive caps. Electrical conductivity signatures can be masked by brine salt mixtures. Radar can detect bright reflections at ice-rock interfaces, but only if the geometry and dielectric contrasts are favorable. Gravity can hint at mass anomalies compatible with liquid-filled basins, but its resolution from orbit requires careful modeling. Seismology is a powerful tool. Listening to how the planet rings can reveal velocity contrasts that. There are, however, clever, non-invasive strategies. Orbital radar sounders with wide bandwidths can probe shallow to mid-depths, mapping layered ice and potential liquid interfaces. High-resolution gravimetry combined with topography can isolate mass deficits or surpluses suggestive of cavities or fluid reservoirs. Electromagnetic induction experiments can sense conducting layers that brine-saturated sediments would produce. In the longer term, particle-based imaging techniques leveraging muons or other natural high-energy particles could reveal density contrasts through kilometers of rock without drilling. Each method trades spatial resolution for reach, cost for safety. The lesson of earlier parts of the inquiry is methodological to meaningfully test the subsurface ocean hypothesis. The ethical dimension runs parallel to the technical one. If a subsurface ocean exists, and if it harbors life, then human exploration would confront a weighty responsibility. Planetary protection protocols already caution against contaminating pristine environments with terrestrial organisms. A sealed ocean is a concentrated epitome of such environments. A single inadvertent microbial hitchhiker from Earth could irrevocably alter a Martian biosphere, erasing whatever independent evolutionary experiment might have been unfolding for millions of years. Conversely, the scientific prize of accessing and studying a second, independently evolved biosphere would be monumental. The knowledge gained could reshape biology, inform the universality of life's chemistry, and recalibrate human understanding of habitability. There is a human reaction that is not purely epistemic but aesthetic and moral. The possibility of subsurface oceans invites a shift in how humanity imagines planetary richness. Civilization narratives are drawn to visible artifacts: cities, plumes, towers, radio beacons. Subsurface ecosystems refuse that theatricality. They embody a humility of existence, life that neither seeks nor expects an audience, organisms whose entire drama is played out in the small places where rock and water converse. To appreciate such life requires patience and a different kind of attention. a willingness to trust instruments that listen rather than cameras that show, and to accept discoveries that arrive as slow accretions of evidence rather than instantaneous. That humility is also a useful corrective to arrogance. Deep time is not impressed by human brevity. An underground ocean, sealed beneath kilometers of rock, would have accrued its chemistry and its habits across eras that make human civilization appear as an instant. The idea reframes exploration from conquest to stewardship. It asks not how quickly humans can extract data, but how carefully they can design missions that preserve what they seek to know. The most ethical approach may be to build observation platforms and non-invasive probes that can return convergent lines of evidence before any physical breach. Listening, acoustically, electromagnetically, gravitationally, before touching might be less glamorous in press releases, but it would be truer to the scale and fragility. Speculatively, if a subsurface ocean hosts communities, the forms of complexity that might arise are themselves a study in constraint and invention. Without sunlight, the selective pressures on signaling, mobility, and storage translate into novel technological analogs, long-lived metabolites as informational molecules, mineral templating as a medium for structural memory, and slow chemical oscillations as the basis of rhythm and synchronization. The technology of such ecosystems could be woven into geology itself, structures of precipitated minerals that store and release chemicals in regulated cycles, networks of conductive mineral veins that channel electrons in place of nerves. These are speculative extrapolations, but they are faithful to a central recognition: life is opportunistic and invention. What binds the scientific, ethical, and aesthetic threads is an overarching modality: patience. The detection of subsurface oceans does not promise quick vindication. It will demand long-term investments in instrumentation, the slow calibration of models, and a tempering of narrative desire. The payoff, however, is rich. Confirming that Mars sustains present-day internal water would alter planetary science, astrobiology, and narrative about life's tenacity. It would enlarge the notion of habitability beyond sunlit surfaces and ephemeral appearances. More quietly, it would restore a sense of modesty, that a planet can be full without shouting, that important histories can be kept in sealed volumes under layers of time. In the end, the idea of subsurface oceans functions as a reminder that planets are striated archives. Their outer skins preserve the vicissitudes of atmosphere, wind, and impact. Their middles record tectonic and thermal history, and their deepest basins can retain fluids and chemistries that are insulated from the noise of surface change. To study Mars only at its surface is to read a single page of a very long book. Listening for and testing the presence of subsurface water is an invitation to turn more pages, to let curiosity extend into depth and duration. If water sleeps beneath the rock, humanity will have to decide how to awaken that sleeping archive. How much to watch, how much to touch, and how to balance the hunger for knowledge with the humility of stewardship. What if intelligence had never learned to look up? What if, on a world where the surface was unforgiving and the sky a harsh place, minds had instead apprenticed themselves to pressure and stone, to the steady heat that bled upward from a molten, restless interior? The image is small and strange, not a skyline of towers and signals, but a lattice of conduits, heat exchangers, and slow-moving machines wrapped in rock. It reframes the question of detectability into something more unnerving. What does civilization look like when its principal currency is not light, but heat, not radio chatter, but low-frequency mechanical whispers, not spectacle, but sufficiency? Speculation becomes useful when it forces rigor. If a civilization evolved entirely isolated from sunlight-born, sustained, and refined beneath kilometers of lithosphere, what physical and technological arrangements would be necessary to make that possible for millions of years? The answer resides at the intersection of planetary physics, biochemical possibility, and long-scale engineering constrained by the stoic arithmetic of energy budgets. The most basic demand is energy. Sunlight is abundant and convenient, but it is not the only energy source in planetary systems. Within any differentiated planet lie reservoirs of heat and chemical potential: radiogenic decay of uranium, thorium, and potassium, residual heat of accretion and differentiation, tidal flexing, where present, redox disequilibria created where hot silicates meet cooler fluids, and geothermal gradients that concentrate power along faults and mantle plumes. For an interior civilization, these become the sun. Their technologies would be those that harvest gradients rather than photons. Consider heat extraction, where a human engineer might deploy heat pipes, thermoelectric modules, or turbines on the surface. A subsurface society would scale those concepts into geological space. Heat conduits, networks of high-conductivity mineral channels or engineered metallic veins, could funnel thermal energy from hotspots into habitable volumes. Thermomechanical engines exploiting phase changes of confined materials could deliver steady power without requiring moving parts exposed to corrosive chemistry. Radioisotopic harvesting, the deliberate concentration and controlled decay of fissile or fertile minerals, could supply baseload energy if handled with geological prudence. Even slow mechanical work derived from tidal flexures or the creep of faults could be coupled to piezoelectric matrices to convert mechanical strain into life, and the technologies built upon it would be profoundly shaped by those rhythms. Biological metabolism in perpetual dark adapts to scarcity and time. On Earth, chemosynthetic microbes exploit hydrogen from serpentinization, sulfate reduction, and radiolytic splitting of water. Whole ecosystems cling to the energy trickle around hydrothermal vents. An intelligent biosphere arising in similar niches would inherit the same economy of scarcity, slow growth rates, emphasis on repair and redundancy, and information encoded into structures that persist under pressure. Memory and long-term storage might therefore favor inorganic crystalline media arrays of doped minerals whose lattice defects carry patterns over geologic time. The technologies of such a civilization would blend the biological and the geological. Material production might be biomineralization writ large, organisms or synthetically guided processes that grow conductive mineral veins, ceramic monoliths, or zeolitic scaffolds optimized for heat exchange and chemical catalysis. Machines could be biohybrid, living tissues that catalyze reactions, mineral matrices that provide structural endurance, and networked microbial consortia that perform chemical synthesis in niche reactors. The notion of a factory shifts. Rather than assembly lines visible at the surface, production occurs within pore networks, in the quiet exchange of ions across membranes. Communication would be a different art. Electromagnetic waves easily escape to space. They are thus dangerous signals for any entity that prizes concealment. Instead, a deep civilization would prefer modalities that travel faithfully through rock. Seismic signaling, carefully modulated mechanical pulses transmitted along crystalline paths, can carry complex codes while remaining effectively localized. Chemical messaging, using gradients of dissolved compounds propagated slowly through fracture networks, achieves durability and privacy. Electromagnetic fields might still play a role, but at frequencies absorbed by surrounding materials, designed to die quickly and not leak outward. Even the rhythms of heat flow could be language, controlled thermal pulses that propagate along. Long-term maintenance is equally critical. Geological and chemical processes operate on timescales that dwarf individual lives, and a civilization that aspires to persist for millions of years would build social structures and technologies aligned to those spans. Redundancy becomes doctrine, multiple independent power conduits, distributed habitats carved into different tectonic blocks, and autonomous repair systems that patrol for corrosion and pressure loss. Cultural institutions would encode patience, protocols to manage resources across millennia, archives intended less for immediate consumption than for eventual reparation and calibration. Memory would be externalized physically into durable mineral records and chemically stabilized, or resource cycles must be closed. In the absence of fresh inputs from atmospheres rich in oxygen or organic carbon from sunlight-driven production, recycling is unavoidable. Biogeochemical loops would be optimized to capture, reuse, and purify every element of value. Waste streams become feedstocks. Carbon, nitrogen, sulfur, and metals are quietly concatenated through microbial reactors and mineral processing plants, scrubbed and reconstituted. In such economies, contamination is not merely an operational hazard, it is existential. Introduced organisms or unregulated flows could upset cycles honed by millennia of selection. Thus, the imperative of concealment shapes so much that follows. Concealment can be strategic to avoid the attention of predatory surface processes like impacts, or ethical, a judgment to avoid altering the surface's fragile equilibrium. Over millions of years, a civilization could cultivate techniques to minimize detectable leakage. Heat budgets can be equalized. Rather than venting energy in spikes that create infrared signatures, engineers could distribute waste heat along large area conductors, smoothing thermal gradients so that orbital thermal imagers see only baseline geology. Chemical emissions can be sequestered in mineral sinks or recycled through catalytic cycles that leave isotopic signatures indistinguishable from abiotic processes. Electromagnetic emissions, when used, the evolutionary pressure toward quietness is powerful. An organism or society that exposed itself would be vulnerable to catastrophes, correlation of activity with surface events, binary interactions with meteoritic intrusions, and the risk that external agents, other civilizations, or natural probes could disrupt closed cycles. Surviving for millions of years would select for the architectures that minimize risk and maximize durability, redundant, modular systems, decentralized cognition distributed across countless nodes, conservative consumption, and an ethic of non-proliferation of detectable signatures. Paradoxically, the very technologies that enable longevity are the ones that hide it. Detectability, then, becomes a serious and technical question. How could external observers test the hypothesis of an advanced subterranean civilization without violating the strictures of contamination and without mistaking slow geological processes for intelligent ones? The answer lies in subtle mismatches, patterns that are improbable under purely abiotic models. A planet-sized heat flux that is locally, persistently modulated in a way inconsistent with standard mantle convection, non-random distributions of mineral deposits that track network geometries rather than natural fracture patterns. Spectral anomalies, particular isotopic ratios of noble gases or heavy metals, consistent with refined high-temperature separation processes rather than purely. Instrumentation must evolve accordingly. Dense seismic arrays, capable of resolving small amplitude, low-frequency signals, could detect patterns consistent with mechanical communications. Electromagnetic induction surveys might reveal conductive lattices running through rock. Muon tomography and neutrino-based imaging promise to peer through kilometers of lithosphere, mapping density contrasts that betray engineered cavities. Chemical sensing of plumes, methane, noble gases, or volatile organics could, with careful isotopic analysis, indicate processing that be artificial. But perhaps the most telling approach is integrative, combining datasets across modalities to identify coherence that is unlikely to arise by chance. There are moral constraints that cannot be ignored. If such a civilization exists, human activity drilling, electromagnetic probing, or even careless orbital surveys could compromise a system that evolved in isolation. Planetary protection principles change in tenor, from preventing backward contamination in the standard sense to a broader stewardship ethic that respects inscrutable biospheres. The choice to probe must be weighed against irreversible consequences. Instruments can be designed to be non-invasive. Long-term passive observation may be the morally preferable path until collective consensus forms. The very act of detection becomes an ethical decision. Does the hunger for knowledge justify the risk of destruction? In the face of deep time, the emotional register of these possibilities is complex. For scientists and the public alike, the idea of an unseen civilization provokes a blend of awe and unease. Awe at the ingenuity required to sustain communities in conditions humans scarcely imagine, unease at the prospect that humanity, for all its noise and visibility, could be oblivious to such a patient intelligence. The feeling is not merely about being wrong, it is about being small. Deep time shrinks human events into instants. An intelligence shaped by geological rhythms will think and act in ways that are as alien to human temporality as a glacier is to a heartbeat. That recognition can recalibrate human projects. The search for intelligence beyond the sky must expand to include the inner spaces of planets. Instruments must be tuned not only to bright signals, but to the art of listening for patterns that unfold over centuries. Ethos must shift from conqueror to custodian, acknowledging that some discoveries are not trophies but responsibilities. The possibility of interior civilizations humbles narratives of cosmic centrality. It insists that intelligence, like life itself, can choose concealment as a form of wisdom. Speculation should not become assertion. The hypothesis that advanced life could persist, hidden from the sun and nourished by core heat and core economies, is not a claim of fact, but a disciplined provocation. It tests the limits of interpretive frameworks and forces a redesign of instruments, missions, and ethics. Whether under Mars's skin, within Earth's mantle, or on other worlds entirely, the lesson is the same. Planets are layered archives, and the most consequential forms of persistence may dwell where sight cannot reach. Science, at its best, will respond to that possibility with patience, humility, and an appetite to listen across scales much vaster than a human lifetime. Why stay hidden? The question lands like a small, sharp stone thrown into a pond of large assumptions. It rearranges the ripples of every search for life and intelligence conducted from orbiters, landers, and radio dishes. If an intelligence exists beneath a planet's skin, and if it has endured across epochs in which surface climates have swung from wet to arid and back again, then deliberate invisibility is not merely plausible, it is often the rational strategy. To ask why they have not appeared is to ask how survival, prudence, and ethics look when projected onto geological timescales. First, there is the blunt calculus of survival. Planetary histories are violent. Giant impacts, catastrophic volcanism, atmospheric stripping events, and nearby stellar flares are not rare curiosities but recurring hazards over millions and billions of years. A society that bases its permanence on the thin layer where weather and radiation play would be betting the future on a fragile margin. In that context, concealment is a form of insurance, retreat, and insulation are practical responses to a world that can, without warning on human timescales, become hostile. Hiding beneath rock or maintaining an existence in thermally stable niches is akin to living in a bank vault when the streets above are periodically raised. It is not cowardice, it is the prioritization of avoidance of conflict follows naturally. In the evolutionary and cultural histories of any complex life form, visibility invites contestation. Whether the contest takes the form of predation, competition for resources, or violent colonization, being conspicuous creates targets. For an underground civilization, the surface can become a theater of unpredictable actors, opportunistic life forms, meteorite-borne spores, or future spacefaring visitors who perceive surface occupation as an invitation. Concealment is therefore a defensive ethic. It reduces the probability of destructive encounters, removes incentives for resource raids, and diminishes the value of their locales to potential invaders. From a strategic standpoint, resource protection is deeper than mere hoarding. Subsurface economies rely on gradients, heat, chemical disequilibria, water sequestered in brines that are both precious and fragile. Exposing these stores risks their exhaustion, contamination, or cultural appropriation. A hidden society could be structured around closed-loop recycling and tight stewardship precisely because any leak to the surface or to the void of space would invite extraction. In that frame, secrecy serves conservation. The fewer discoverers, the lower the risk that valuable geothermal currents or mineral seams will be disrupted. This is not an act of parochial greed, but of planetary prudence. There is also the risk of contamination in both directions. Surface organisms, whether microbial or macroscopic, carry chemistries and metabolic strategies that could upset carefully balanced subsurface cycles. Earthly analogs are instructive. Introducing alien microbes to a pristine cave system can catalyze biofilms that alter mineral precipitation, change gaseous equilibria, and collapse long-standing ecological niches. Conversely, an underground biosphere, if it exists, might harbor chemistries incomprehensible to surface ecologies. Surfacing or cross-contact could be catastrophic. A policy of non-contact, enforced through concealment, is a form of biological quarantine. It is the ethical equivalent of closing a hatch, but concealment can be an ethical choice as much as a practical one. The deep intellect that survives through millennia may cultivate a non-interventionist philosophy, analogous to human concepts of stewardship and sanctuary. If surface evolution is underway on a different timetable, intervention could be disruptive in ways that go beyond survival. It could erase emergent cultures, alter evolutionary trajectories, or impose foreign technologies and values. Concealment then becomes an expression of respect, an agreement with oneself to observe rather than to convert, to study rather than to convert, to study rather than to dominate. Seen through this lens, not appearing is not hostility but restraint. Temporal asymmetry plays a decisive role as well. Civilizations that reckon in millennia have no imperative to rush contact. Their planning horizons extend far past the fleeting eras of other societies. For them, waiting is not a lack of courage but a design principle. Observe, gather data across cycles, test for stability, and only act when uncertainty is sufficiently reduced. Time is a tool for risk management. Appearances and contacts that to humans seem overdue may simply be misaligned with a strategy that values accumulation of long-term knowledge over immediate recognition. A patient intelligence may prefer the slow accrual of evidence to the spectacle of sudden revelation. Concealment is also an energy economy. Be conspicuous, and one spends resources broadcasting, maintaining visible infrastructure, and defending exposed assets. Be quiet, and resources are conserved, recycled, and dedicated to maintenance across ages. The engineering implications are profound. Power systems minimize detectable leaks, waste heat is distributed and diffused so it does not betray a concentrated source, and communications are localized or bound into conduits that do not radiate into space. Silence is efficient. It is energy invested in longevity rather than display. Technological choices follow from these imperatives. If visibility invites risk, then technologies are deliberately designed to be non-transmissive. Communications might use mechanical signaling that travels through rock rather than radio frequencies that leak into orbit. Power distribution could be embedded in mineral veins whose electromagnetic signatures closely resemble natural conductivity profiles. Materials processing might mimic abiotic fractionation so that isotopic fingerprints appear indistinguishable from natural processes. Concealment in practice therefore becomes an art of blending engineering into geology, altering a planet not to announce life but to make life indistinguishable from rock. Observation, however, is not mutually exclusive with invisibility. The very act of concealment presupposes an intention to watch. A hidden intelligence that cares about survival will monitor outer layers, the surface, and the space above, with great care. They may observe humanity's signals without returning them. They may track infrared signatures, orbital traffic, radio leakage, and the chemical signatures of atmosphere and soils. Their sensors could be seismic arrays tuned to the frequencies of human industry, muon or neutrino detectors that read the mass flows of orbital craft, chemically sensitive matrices that detect synthetic compounds in microquantities escaping into the lithosphere. Observation can be intimate and patient. From this vantage, Earth's broadcasts, radio waves, radar, bright night sides are as noisy and rude as bonfires. A subterranean observer could classify human activity along multiple axes: abruptness, intent, concentration, and contamination risk. Our explosive demonstrations, rocket launches, nuclear tests, rapid urbanization are signature rich and easy to quantify. Slow, distributed trends. Incremental greenhouse warming, gradual mining, the subtle mixing of isotopes are more difficult to interpret and may be met with a conservative approach: monitor, but do not assume hostility. In part, a hidden intelligence's reluctance to appear could stem from this interpretive caution. Signals are ambiguous. Anthropology on cosmic timescales suggests cultural reasons for hiding as well. Some societies prize the autonomy of isolation, others fear the moral corruption that unchecked contact can produce. The memory of catastrophic contact in a deep culture's own history episodes where external actors destroyed habitats or stole technologies could harden into taboo. Concealment then becomes a cultural norm, enforced not just by architecture but by moral narratives, myths that sacralize the crust as a sanctuary, laws that punish exposure, rituals of surveillance that create collective responsibility for secrecy. Over millennia, such norms could be as binding as environmental regulations are for humans today, if not more so. Game theory offers a formal logic to these intuitions. In multi-agent systems with asymmetric capabilities, signaling vulnerability is costly. The payoff matrix favors hiding if the cost of being discovered outweighs the expected benefits of contact. This remains true even with altruistic players. Without credible assurances that an outside party will reciprocate non-exploitation, rational actors minimize leakage. If the probability of destructive contact multiplied by the expected damage exceeds the value of potential cooperation, the equilibrium is secrecy. This calculus has practical implications for how humanity should approach discovery. The instinct to announce, to reach out, to claim kinship is powerful and historically ingrained. But if an intelligence can plausibly choose secrecy for the reasons outlined — survival, resource defense, contamination avoidance, ethical restraint — then humanity's approach to searching must be calibrated. The ethics of detection and contact must be tempered by humility. Aggressive probing, intrusive drilling, or the careless broadcasting of targeted messages could be perceived as breaches of sanctity, and even well-intentioned contact attempts could do irrevocable harm. A responsible strategy for humans would therefore emphasize patient, non-invasive observation, cross-checked by multiple modalities, and accompanied by international dialogue around stewardship. It would privilege low-impact sensors, remote listening campaigns, and the systematic modeling of how our signals propagate through planetary systems. It would also involve rethinking planetary protection not as a set of sterile technicalities, but as an ethic aligned with the possibility that advanced non-human intelligences might choose not to be found. There is an emotional dimension to this hypothesis that resonates deeply. The idea that another mind might be watching, measuring, judging, refraining, elicits a mix of vulnerability and accountability. It reframes humans as performers of a kind we may not fully recognize. Our nightlights, our heat plumes, our chemical signatures are public acts in a theater where the audience is hidden. That recognition can be unsettling, but it can also be ennobling. The possibility that a more patient intelligence exercises restraint invites humans to cultivate their own restraint, to consider the long-term consequences of their technologies, to build institutions that steward rather than exploit, to listen before acting. Finally, stealth has aesthetics. Concealment is not only a tactical choice, it is an expression of a different kind of civilizational maturity. A society that finds ways to fold its existence into the rhythms of a planet. Mining heat without leaving cracks in the armor, maintaining knowledge across epochs without public monuments, communicating through the hush of stone, demonstrates an alternative choreography of intelligence. It values endurance and subtlety over spectacle. For human observers, acknowledging that possibility widens the imagination. Intelligence need not be ostentatious to be profound. In the end, the question, why stay hidden, opens more than a tactical ledger. It opens a moral project. It asks what kinds of beings humans wish to be in the cosmos. If concealment is an evolved strategy for survival and ethics under planetary constraints, then the lesson is simple and disquieting. Sometimes the most impressive civilizations are those that never announce themselves. Their refusal to appear is not a snub, but a choice, one that invites humility, a reorientation of search strategies, and a slow cultivation of patience that matches the deep time in which they have learned to thrive. What if the planet's skin were not a display but a curtain, not an invitation to inspect, but a defensive gesture? That image flips a deeply held assumption that the surface is the place where truth waits to be read. Instead, the dry, cold, iron-stained crust of Mars can be imagined as a natural wall, a composition of particles and rock that muffles, scatters, and absorbs the signals by which distant observers try to know a world. The question is small and precise, yet it carries an uncomfortable weight. Perhaps the silence humanity reports from the red plains is not emptiness but the effective work of a very good shield. Physically, the surface is a complex material. Millimeters of dust, centimeters of loose regolith, meters of compacted sediments, and stretches of basaltic lava flows form a layered palimpsest. Each layer has its own porosity, grain size, and mineral chemistry. Each transforms incoming light and outgoing heat in subtle ways. Sunlight that skims the dunes is scattered into a million directions, photons losing coherent information about what lies beneath. Radar pulses that might have penetrated smooth ice are jammed by rough textures and by the electromagnetic properties of oxidized iron. Thermal signatures that could betray warm flows are diluted by the low conductivity of powdered regolith and by the slow heartbeat of subsurface heat. Taken together, these mundane properties remote sensing instruments are elegant and blunt at once. Optical telescopes collect photons that have reflected off the skin and present those reflections as maps and colors. Infrared imagers read surface temperature variations. Spectrometers catalog mineral fingerprints in reflected light. Radar sounders send radio pulses that listen for echoes from interfaces below. Seismometers translate tiny shakes into the language of structural layering. Each method is tuned to a particular class of signal, and each is fundamentally biased toward the outermost strata. Photons rarely reveal what lies under meters of dust. Radar struggles when the upper few hundred meters are irregular and electrically complex. Seismic waves tell of there are granular, almost tactile ways that the surface acts as shield. Dust devils, those modest whirlwinds that make ephemeral tracks across the plains, are not mere curiosities. They are dynamic erasers. A rover's path, the faint scars of a lander's descent, the subtle discoloration of a chemical outcrop. All can be leached away by a season's worth of wind. Solar panels that once glinted are painted over by decades of grit. Micrometeorite gardening churns the topmost layers, exposing fresh minerals to the oxidizing regolith and removing clues that might preserve organics. The very processes that make a planet superficially recognizable also act like a slow sandstorm that buries nuance and erases the calligraphy of history. Electromagnetically, the skin is a complicated medium. The dielectric properties of basalt and iron oxides, combined with high porosity and variable moisture content, scatter radar waves and attenuate high-frequency signals. Signals that might escape from a buried volume are subject to multipath interference and lose coherence. Reflections fragment into clutter that can be mistaken for noise. A thin layer of saline brine, if present, can swamp a spectral signature by absorbing certain wavelengths. At certain frequencies, a regolith can act almost as a blind. Outward-directed emissions are damped and inward-directed probes return muddled echoes. It is a banal, physical reality with disproportionate consequences. The wrong wavelength, the wrong incidence angle, or the thermal shielding is equally effective but more subtle. Heat generated in the deep, whether from residual planetary differentiation, radiogenic decay, or localized chemical reactions, finds a tortuous path to the surface. Regolith's low thermal conductivity and insulating porosity mean that subsurface anomalies are smoothed by conduction and dispersion. Diurnal temperature swings affect only the uppermost centimeters. Thermal inertia hides deeper signatures behind a slow, patient veil. Heat may rise along conduits and be distributed across wide areas, losing its fingerprint in the process. The effect is analogous to muffling a voice behind thick curtains. Energy is not absent, it is merely redistributed until it no longer betrays. Rovers and landers, the most intimate instruments humans have placed, are themselves subject to the limits of aperture and scale. A single soil scoop samples a teaspoon from an area the size of a living room within a planet that is continental in its span. Wheels trundle over microenvironments, stirring and mixing as they go, but the sampling bias is irremediable. Human-made machines touch what they can reach, not necessarily what matters. The logistical choreography of landing sites and traverses is dictated by safety and energy budgets, which privilege flat plains and gentle slopes over the fractured, potentially more revealing terrains. The consequence is a patchwork knowledge, brilliant in its local fidelity but patchy in its planetary representation. The shield works also by constructing plausible false negatives. Bright radar reflections under polar caps, layered signatures in neutron spectroscopy, and heat anomalies can all be read with reasonable abiotic interpretations. Is an anomalous echo a sheet of liquid water, or a contrast between ice and dust? Is episodic methane release a biological whisper, or a mineral outgassing triggered by thermal fracture? The surface offers many ways to explain away the unexpected. A mineral sink can bind the gas, a layer of permafrost can trap a vent, a crustal cap can smooth a geothermal plume. Observational conservatism, a virtue of good science, can thus play into concealment. The most parsimonious interpretation, given the limited data, is often there is a psychological cadence to this reality. Scientists experience a cascade of emotions when confronted with data that might be meaningful but could also be an artifact. The first reaction is the electrical thrill of possibility, a spike of curiosity that quickens the pulse. That is followed by the technician's skepticism, cross-checks, simulations, and the search for mundane explanations. If anomalies persist, humility arrives, slow and insistent. Humans are prone to narrativize. They like tidy stories with protagonists and climaxes. The shield disturbs that desire, insisting that the narrative must pause and expand to accommodate uncertainty. That discomfort is not a defect, but a disciplinarian force. It leads to speculation about deliberate camouflage, that a subsurface intelligence might employ the surface as an active cloak, shifts the frame from physical to strategic. If a community would prize longevity, it would prefer to minimize detectable emissions. Heat flux can be equalized along broad networks so that orbital thermal imagers see only the slow geologic baseline. Chemical effluents might be channeled into mineral traps that present isotope ratios indistinguishable from abiotic processes. Communication could be confined to mechanical pulses moving through crystalline conduits or to electromagnetic bands attenuated by surrounding rock. Those strategies are not mystical, they are engineering rationales built on the same physics humans use. The irony is time, again, is a crucial ally of concealment. Human missions are snapshots, episodes measured in years or decades, set against planetary clocks that tick in millennia and millions of years. A subsurface system that modulates heat on century-long cycles, that releases gas in events separated by thousands of years, or that repairs disrupted pathways slowly will appear inert to a sequence of brief visits. The surface can act as a slow filter. Events transpire below but are mixed and averaged before their signals reach instruments. In that sense, the shield is temporal as well as material. It privileges long, patient processes over the bright and sudden. Understanding the protective role of the surface has practical consequences for exploration. It argues for instruments designed to pierce the veil in different ways. Long baseline seismic arrays that can resolve scattering and resonant modes, low-frequency radar capable of penetrating deeper under favorable conditions, particle-based imaging, muons, neutrinos, that can infer density distribution through kilometers of rock, in situ drilling with unparalleled sterilization standards. Each approach has trade-offs in cost, resolution, and risk. Together they form a response that respects the surface's duality. It can be an archive to read, but only with the right tools and a discipline of patience. Ethics enters the picture inexorably. The surface does more than hide, it protects. Above it may lie a fragile equilibrium, and below it may be reservoirs of chemistry, archives of past climates, or even potential ecosystems. To breach the shield is to undertake an act of profound intervention. Planetary protection protocols, the rules and norms that govern forward contamination, are not merely bureaucratic, they are the recognition that some layers of a world deserve stewardship. The possibility that the surface keeps a secret also imposes restraint. The impulse to drill deep or to shout signals into the void must be balanced against the risk of irrevocable harm. That moral hesitation, ultimately, the surface as shield is as much an epistemic lesson as a geological fact. It undercuts the comfort of seeing, insisting that absence of evident signals is not evidence of absence of content. It recasts a planet's outer crust as a politics of revelation and obscuration. What is visible is curated by processes both natural and possibly intentional. What is concealed calls for different methodologies and a different humility. For observers, the implication is both technical and affective. Instruments must be diversified and missions prolonged. Narratives must be held in suspension. Wonder must be coupled to caution. The image closes not on triumph, but on an ethic. If a planet chooses, through its skin, to be private, then the proper human response is not louder noise, but quieter attention. It is to design ears that listen in new registers, to assemble patient campaigns that stitch together multiple modes of evidence, and to cultivate a restraint that honors the planetary scale. The surface that shields is not merely a barrier to curiosity, it is an invitation to change the terms of curiosity itself. From spectacle to stewardship, from the instant to the epoch, from conquest to careful listening. In that shift, humility becomes the central instrument of exploration. What would it mean, in the quiet ledger of deep time, for a world to harbor technology that outruns human craft by millennia? It is a question that begins with a physical fact and ends with a moral one. On planets large enough to be geologically active, heat and pressure are not hazards only. They are resources, slow-moving rivers of power and process. To imagine a civilization that learned not to flee from those forces but to partner with them is to invert modern assumptions about what technology must look like. It need not consist of gleaming towers and radio hymns. It could be an economy of conduits, a choreography of thermal and material flows, and a repertoire of techniques tuned to the physics of stone and metal. At the most basic level, the engineers of an interior civilization would have solved a problem that earthbound humans are only beginning to approach in small, tentative ways: how to manipulate and stabilize planetary scale heat. On planets with active mantles and decaying radiogenic isotopes, the interior continuously produces energy. The trick is not inventing energy, but managing its distribution. A civilization that mastered that management would possess what humans casually call unlimited energy, a steady, accessible flux sufficient to power sensors, computation, material processing, and transport for epochs. But unlimited in this sense is not a mythic engine unmoored from thermodynamics. It is a disciplined exploitation of. Imagine, for a moment, a quiet apparatus embedded in a crustal seam, a lattice of high conductivity veins grown or sculpted into the rock, each vein acting like a geothermal heat pipe on a planetary scale. Heat from a mantle upwelling is directed into these conduits. Within them, phase-change materials circulate deliberately, salts and alloys that absorb latent heat at depth and release it at controlled nodes. Turbines are unnecessary. Instead, the civilization uses reversible thermochemical engines. Materials change, form, and recombine in closed cycles, the chemical enthalpy harvested to run microfabrication arrays and to pump fluids that keep tunnels pressurized. Control of a planet's core climate follows from that same logic. On human timescales, the word climate evokes atmosphere and weather. But for a civilization that operates in lithic domains, climate is a broader concept. It includes the thermal state of the mantle, the distribution of melt, the conductivity pathways through the crust, and the magnetic behavior generated by convective currents in an iron core. To nudge these processes is to tilt planetary destiny. The mechanisms are subtle. Deliberately increasing conductivity in certain crustal corridors can shepherd heat flow away from vulnerable regions, lowering the probability of catastrophic volcanism. Conversely, injecting catalytic minerals into a plume axis could stimulate localized upwelling that maintains a stable thermal gradient where habitation. Such interventions would require uncanny material mastery, metals that behave predictably under the crushing pressures of tens of kilometers of overburden, ceramics that conduct heat efficiently while resisting creep, engineered microbes or mineralizing organisms that grow structural veins without catastrophic brittleness. Geological processes are slow and massive. Engineering for them is a craft of patience. Any change must be reversible, or at least fail, safe, because a misdirected thermal pump on the wrong timescale can set off chain reactions, fault unlocking, runaway melt migration, or the loss of volatile inventories. The moral calculus of planetary engineering, therefore, is inseparable from its technical side. Power, once harnessed, opens possibilities that a surface-bound civilization might mistake for magic. With regulated heat and controlled chemical gradients, synthesis at scale becomes feasible within the protective envelope of rock. Minerals can be purified in situ. Superconducting filaments, grown along cooled channels, could distribute power with vanishing loss. Arrays of crystallographic memory could store information for periods that make human archives seem ephemeral. Material production is not a factory lined with conveyors, but a kind of geological cultivation, accretion chambers, where atoms are coaxed into lattices, where structural components are precipitated and annealed under pressure, then assembled by machines part inorganic, part biological. Movement through such a world would likewise be adapted to the environment. Surface roads and skyways are irrelevant in domains where the skin of a planet is a barrier. Instead, vast networks of tunnels, sometimes natural, sometimes deliberately expanded, become the arteries of civilization. These are not the claustrophobic caves of human intuition. They are engineered megastructures, calibrated for strain and thermal dynamics, arching corridors tens to hundreds of meters across, lined with composite skins that flex with tectonic motion. Pressure-sealed conduits with active damping systems that smooth out microseismicity. Transit arteries where vehicles ride on trains of staged phase transitions, gliding through vacuum or low pressure. The design language of these tunnels is telling. They're built for longevity and maintainability. Materials are chosen not for low cost, but for durability under migration of stress and chemical attack by brines and volatiles. Where transport is regular, self-healing walls are grown, layers of bio-mineral composites that respond to cracking with localized precipitation. Where rapid movement is required, magnetically levitated pods slide through low-resistance channels, their fields shaped and absorbed by surrounding superconductive linings, so they radiate almost no electromagnetic signature outward. Lighting is not bright spectacle, but functional. luminescence generated by chemosynthetic organisms, or photonic channels that guide light from geothermal lamps at long wavelengths which do not escape. These technical achievements, however, have a detectable shadow. No matter how carefully a civilization calibrates its emissions, engineering on planetary scales will leave traces, if one knows where and how to look. A network of high-conductivity conduits, for instance, subtly alters a planet's thermal map. Satellite-borne thermal imagers might register a slight smoothing of heat anomalies where hotspots have been distributed broadly rather than concentrated. Gravimetric surveys could reveal density anomalies consistent with engineered veinwork, repetitive linear patterns that resist attribution to natural faults. Low-frequency seismic noise might show non-natural temporal regularities, rhythmic signals whose statistics differ from stochastic tectonic tremor.